Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, so for this week, we will learn about chapter 3, digital transmission. In previous chapter, which is chapter 2, you already learned about data and signals. So we learned that data can be represented in a digital form or analog form, and also signals can also be um, represented in analog or digital form, right? So if you still doesn't clear about that concept, you can refer to my lecture. I already uploaded to YouTube, right? So in this chapter, we will learn how we going to transform, or how we going to use digital transmission to transmit analog or digital data. So data, we transmit it to the receiver using a digital transmission. Okay. Right. So in this chapter, it's cover digital to digital conversion, right? From digital data, if we want to use digital transmission, so we just use digital to digital conversion. Or if we have analog data, such as a telephone, voice, right? If let's say we use analog telephone, and we want to use a digital transmission, so we need to convert from analog to digital conversion. And if we use digital transmission, what is the transmission mode? So that is what we will learn today. Right, first thing first, we'll talk about line coding, right? So line coding is a process of converting a sequence of digital data to digital signals, right? So the data is digitals in the form of binary ones and zeros, right? And we transmit it using a digital signals. Okay. So we can see here the computers, the data is represented in zero or ones. Maybe it is an integer, or for examples, or maybe it is a file, right? So we use an encoder. So we transform it into digital signals. Then the receiver, we use a decoder to decode back the data and receive back the data. So usually line coding is being done when we use a modern computer system, right? For examples, we have let's say we go using a local area network. So our PC want to try to send a data to another PC, and we are using the LAN. So probably it using a line coding to transmit the data. Right. So we also need to know the signal element vs data elements, right? So signals and data, what is signals element and what is data element, right? So data elements is also known as data levels. So data elements is actually a number of values used to represent the data. Okay. So smaller entity to represent information what are needed to be sent. So actually it's the data. For examples, let's say we want to the data is an ASCII form. ASCII form is for examples, let me open up my browser here. For example, ASCII. You see from here. Yeah, so for example here, the ASCII code. So for example, you want to send a character A, so it actually represented in hexa 41. So if we convert it into binary, so it is actually 0100 So it is in a, so how many data element? So it is actually we have 8, right? So that is what we want to send. And the signal level is the number of values allowed in a particular signals. For example, in one, let's say the data that we want to use a signal. So let's say in one period of the signals, how many data we can cram in to to transmit the data. So data element are being carried and signal element are the carrier, are the one that carries the data in terms of digital signals. Okay. So we can see from number A, okay, so we have let's say one data element 0, right? So here we have three data element 1, 2, 3, right? So for example, for one data element 0, it can be sent for one signal element, it can carry one data element. So if we can see for B, so for examples, uh, one data element, right? So it need to be sent by using two signal elements. So for example, so that's mean that the digital signal is changing two times, only it's represented 0. So this is not very efficient, right? So this one is more efficient. For example, we have two data element, which is 0 and 1s, but we can send it by just using one signal element. So this is more efficient. So the one that we want is we must have less element, but we can send more data because we always want to send more data. So for data limit, so that means we have R equals to 2. Okay. So R represent data element, right? So or um we have four data elements, but in order to send it, so we need three signal element, maybe three transition in the signals. Only then we can represent 1, 1, 0, 1. So R equals to 4/3, right? Okay, signal element via data element. So this is more discussion about it. So a part of signal that is distinguished by a duration, magnitude, right? So the signal element, I mean, if let's say it's up, down, so maybe one up, one down, maybe it what we call it as one signal element, or it depends on the encoding. We will learn later on about the encoding of the signals, right? So relative position to another element, transition from one signal state to another signal. So for data element is the basic unit of information built on standard structures having a unique meaning and distinctive units or values. So that is data element. Okay, so for example, we see this example. So later on, in our tutorial class, we will more hands-on on our tutorial. We will do more on this question, but for during this lecture, let's see these examples. A signal is carrying data in which one data element is encoded as one single element. So that's mean R equal to 1. So one data element can be sent with one single element. So if the bit rate is 100 kilobit per second, okay, so what is the average value of a baud rate if C is between 0 and 1, right? So assume the value of C is 1/2, okay, between 0 and 1, so there is actually 0.5. So 0.5 is 1.2. So how we calculate the baud rate? So it one the baud rate, right? So the formula is C times N times 1/2/R. So R we have 1, right? Okay, so N is 100 kilobit per second. So first we need to convert it into bit per second. So kilo is actually 100. So we add 3 zeros here. Okay, so we just substitute C 0.5, 1.2 times 100,000, and we get 50,000 baud. So we want it in kilobaud, so we get 50 kilobaud. So we convert it. Okay, so please see in my previous lecture in chapter 2 how we're going to convert bits from bits, kilobit, right? Okay, so how are we going to convert it? Okay. Okay, next, data rate versus signal rate. So data rate is equals to bit rate. So number of data elements sent in 1 second. So in bit per second. So that is what we known as bit rate. For signal rate or pass rate, modulation rate. So that's mean a signal element sent in 1 second. So for data rate, how many data can be sent from sender to receiver? So that is a bit rate. But for signal rate, how many signals change can be done in 1 second, right? So in data communication, so if we increase the data rate, of course we increase the speed of transmission. If we decrease the signal rate, we will decrease the bandwidth requirement. Okay. Okay, so another thing is in line coding, there is some what we call as a problem, right? So this is always this problem is always played in the line coding because usually in digital transmission, it's usually been transmitted using a DC component. Mean is using a DC power, right? The electrical, we have AC and DC, right? So, okay, so um, we have what we call as residual direct current component. So it is an undesirable component which DC component can cause a distortion or create errors which it does not allow operations of DC component. So uh, extra energy residing on the line and it is a useless. So it will cause a distortion and error. So for example here, so this is with DC component and this is without a DC components, right? So it can occur when a voltage level in the digital signal is a constant, so spectrum create a very low frequency, and it probably occurs if we pass the low frequency, right? So if we have a DC component, so sometimes it will create a unnecessary distortion and error. So that is a DC component, right? Okay, so one more thing, in order to avoid having an error, so usually in line coding we include synchronization so that the synchronization can be used by the receiver to ensure it is receiving the correct information that the sender want to send. For example, the sender want to send bit 1001, right? 1001, that is the sender actual message. So maybe along the line when it's use a digital transmission, so maybe there is a DC component error. So maybe it is getting distorted or there is extra energy there. So that's why we need a synchronization so that the receiver can see, oh, okay, so this is actually uh, um, a transition, so it can knows that, oh, okay, this is the beginning of one, or maybe this is the beginning of zero, some examples, right? So here this is a normal one, 1010. So maybe the lack also, for example, if it's lack of synchronization, so it doesn't know when the ones begin or when the zeros start. See, right? So that's why we need a synchronization. And later on in the digital encoding, we will learn how we can provide some of the encoding can provide synchronization using its technique or method. Okay. So the line coding, we have a several schemes. So this is the encoding, how we represented the data, the ones and zeros in the data, in the signals, in the digital signals, right? So line coding, we have first first type is the unipolar type. So the example of the implementation of unipolar scheme is NRZ, non-written zero. For polar, we have non-written zero or written zero. Biphase, we have Manchester and diffusion Manchester. For bipolar type, we have AMI or pseudo-Terney. For multi-level, we have 2B1Q, 6B60, 4D PAM5. For multi-transitional, we have MLT3. So here, the most famous one is Manchester and differential Manchester. Okay, let's see the unipolar. So this is the most simple and primitive, and usually these also always have what we call as DC component problem, and it doesn't have any built-in mechanism to provide synchronization. So we can see how it is. So if the we want to send a value of 1, So the signal will become a positive value. So if we want to set a 0, the signals will have a 0 value. So it's number 0, so it is 0. So 1, it will become a 1. See? 0, 0, 1. So this is the most basic kind of encoding we can use in digital transmission. But since it just have only one level here, right? So it's always have been plagued by DC component and its lack of synchronization. So there is no additional way. From here we can know when the 0 start or um, 1 start. Okay. And next we can see another type, which is polar. So we have unipolar, right? And now we see the polar type. So in polar type of encoding, we have, instead of just one level, so for unipolar we only have positive if you want to encode 1 and zeros. So here for unipolar we have positive and negative, right? So unipolar, the implementation is NRZ encoding, RZ, Manchester, and differential Manchester. So we can see the first one, non-written 0 for NRZ. Okay. So for first, for NRZ encoding, the value of signal is always either positive or negative, right? So it will not return to 0, right? Maybe to avoid to alleviate the problem of DC components, right? So the first one is non-written 0 levels. So the level of signal depends on the type of bit that is represent. So if we want to send 0 bits, so it will have a positive value. So if it is a 1 bit, so it will be a negative value. And for NRZ I invert, if we want to encode 0, so that means there is no changes in the signal levels. So or if we want to send a 1, there will be a transition from positive to negative. So it is different from NRZL, right? So let's see the examples. So let's say NRZL. So from here, it says that 0 is positive value, 1 negative value. So this is straightforward. So 0, it will show a positive, right? So if it is 1, it will have a negative voltage. You see, right? So 1 negative 1. Okay, so on contrary, so if we want to use NRZI, so for 0, no changes. For example, 0. So they say it start from 0, so no changes. So when it say it's know that okay, the next bit is 1, so it will inverse, it will go down. So when it sees the next bit is 0, so no changes, so it just straight away. So 0, no changes straight away. So it see, oh okay, I want to send 1, so it will go back up to positive values. So next is 1. Oh, I need to invert back because it must be a inversion, right? If we want to send 1, so next is 1, so I invert back. So next is 0, so I just no changes. So just keep the voltage level. See, right? So please see it and please understand it. We will do more later during our tutorial. Okay, so in RZL, the level of voltage determine the value of bit. So in RZ, the inversion or the lack of inversion determine the value of bit. And RZL and RZI both have a DC component problem. Okay. So now we see what we call as return to 0 encoding. So it now for bipolar, it have positive and negative. For return to 0, it basically have 3 values: positive, negative, and zeros. Right. So if we want to represent once, so it will return from positive value to 0 values. So if we want to represent zeros, it will um, go from negative to 0. So advantages is it occupies more bandwidth, because you see here for one data elements, it need 2 signal elements. So 1, 2. See, we need 2 signal element, but we can only represent one data. It is said to be most effective when compared with three alternatives before this, because it doesn't have, maybe it doesn't have a DC component problem. And the transition here in one signal element can be used for synchronization, right? So for example here, for 0, so it will form negative to positive. So if you want to represent one bit, so it's positive to here, positive to 0. Okay, see? So if 1 0, so from negative to up here, so again, if we want to represent a negative value, so negative 0 value, so in negative to 0, and so on, right? Okay. So next, so this is a famous one, Manchester. So use an inversion at the middle of each bit interval for both synchronization and bit representation. So binary, if you want to represent a 1, so it's negative to positive. If we want to represent zeros, it's positive to negative. All right. So if you see, so if it's a 0, it will the signal will become like this signal pattern. So if you want to represent ones, the signal pattern is from negative to positive, right? So here. So you see, this is more effective when compared with return 0, because it doesn't require much bandwidth, because we only have one signal element, and it can have send one data element. So for example, if we want to represent zeros, so it's one positive, two negative. So if we want to represent one, it's from negative to positive. So 0, see, okay. So next, we also have what we call as differential Manchester. So the equation of the middle is used for synchronization, right? So for examples, if the next value is 0, okay, so it will transition here, okay, see transition. So it's 1, so no transition, so it just usual. So see, so if it's 1, it actually it will just go straight, but since it is a 0, so it need a transition at the beginning, so it will transit. Dia akan naik atas tu, kita akan naikkan ke atas macam ni. So tengok, oh ada 0 lagi, so dia transit lagi naik atas. Okay, kalau once, so nampak dia straight je kat sini. Okay, right. Present of transition at the beginning of a bit means 0. Right, itulah differential Manchester encoding. Okay, so in Manchester and differential Manchester encoding, the transition at the middle of the bit is used for synchronization, right? So there also doesn't have DC problem. So the minimum bandwidth of Manchester and differential Manchester is 2 times of non-return 0. 2 times, okay, because we only need one signal element to send one data element. Okay. Next, we have bipolar. So in bipolar, it has a 3 voltage level: positive, negative, and zeros. Okay. So the common bipolar encoding is known as bipolar alternate mark (AMI). Okay. So from here, for bipolar, we can see for in MMI. So if we want to represent zeros, so 0 means 0 voltage. So 1, it will alternate between positive and negative. Okay, we can see here, if 0 is 0, so if 1, it first inverse to positive. So 0, it will continue to 0 value. So next, if you want to represent 1 again, so instead of positive value, it will inverse to negative value. So next is also 1, it will again inverse back to positive value. Right, it will alternate between positive and negative to represent ones, a bit of 1. Okay, next, we also have a multi-level scheme. So the reason why we have this scheme, they introduce it because it want to increase data speed and decrease the required bandwidth, so that we can have a better transmission speed, but in the same time we have minimum bandwidth requirement. So increase number of bit per bar by encoding a pattern of m data element into pattern of n signal element. Okay. So example is 2B1Q, right? You can see here this is a multi-stationary MLT. So from here, So US3 signal level, so we have positive, okay, so we have positive 1, 0 and negative 1. So signal transit at the beginning of 1 bit, no transition at the beginning of 0 bit. Okay, so 0, yeah, so if 1 it will transition, okay, dia naik atas. So since the 0, so no transition, so 1 it transition back to 0. So 1 again, so it transition back to negative. So 0, no transition. Okay, 1 again, so it will transition to 0. 1 again, so it transition to positive. 1 again, it transition back to positive. See, so 0, no transition. Every time there is 1, we want to encode 1, it will transition from, let's say, from positive to 0, so from 0 to negative, or from negative to 0, 0 to positive, right? Okay, so when we summarize all the encoding scheme, okay, so we can see that for unipolar, it is costly because it need more bandwidth to send one signal, so no self-synchronization, right? And it has a DC problem. For NRZL and I, also no self-synchronization and also have a DC problem. For bipolar biphase, right? So it has self-synchronization and no DC problem, and it has high bandwidth. So bipolar MI, it has no self-synchronization and has a DC problem. For multi-levels, right? So we can see here. So this is the characteristic and maybe the advantages of using such encoding. Okay, so next, in order to further improve line coding, the scientists or the engineers introduce what we call as block coding. Okay, so now in order, let's say kan, kita nak send macam tadi 1001 from sender to receiver, how to make sure that ensure that the data is not corrupted while we transmit, because we have a DC problem, right? We have synchronization problem. So they propose what we call as block coding. Okay, so it add another bit so that the bit can be used to detect an error, right? So the process is, first it will divide the bit. So let's say we want to send 32 bit. So actually the 32 bit will be divided into, let's say, four bits group. So maybe the 32 bit is divided into a group. So each group will have a 4 bit, for examples. Then the 4 bits group is being substituted into its mapping. So dia akan substitute lah. So 4 bit tu akan jadi 5 bit. Tapi dia ada cara mapping. Dia ada table. So lepas dia dah buat the division and substitution, dia dah arrangekan into groups and dia dah substitutekan bit binary tu, baru dia gunakan line coding yang guna itulah, either Manchester ke, unipolar, bipolar, multi levels, right? Baru dia transmit the digital signals. So the step is, first we divide it. So simple of it is divided into group of m bit. So substitution is we substitute the m bit code into n bit group, right? So for example, 4B to 5B encoding, and only when we want to use a digital transmission, so we use a line coding lah, ni unipolar ke apa. So we can see here, to substitute, right, for 4 bit to 5 bit block, dia memang ada table, right? Itu nama dia block coding. So contoh, let's say untuk yang data 0001 dalam 4 bit tadi tu, so actually dia akan convertkan kepada 1110. So bila receiver dapat, dia kena tengok balik table dia lah. Baru oh okey ni, baru dia kena decode balik, right? Okay. And also in block coding, dia ada codes dia. So mungkin kalau dia send kan, kalau dia send 00, maksudnya quiet, dia tak nak send apa-apa. Kalau idle 111, hot 0010, itulah supaya dia boleh send signal dalam transmission dia tu. Supaya supaya receiver tu tahu, oh apa sebenarnya sender nak buat, apa dia nak hantar, nak set ke, nak receive ke, okay? Alright, so this is more better. So there is also alternative to 4B. This is, we see 4B to 5B blocks. So we also have 8B to 10B, right? So similar, almost similar, but instead of grouping it into 4 bits, it group into 8 bits and it substitute it into 10-bit code. So lagi besar lah, lagi panjang, lagi macam. So more error detection capability than 4B dan 5B. Dan tadi kita hantar 5 kan, so dia ni ada hantar 10, right? Okay, so also we have 8B60, so designed to substitute an 8-bit group with a 6-symbol code. So each symbol is ternary, so having one of 3 signal levels. So each block 8-bit is encoded as unit of ternary signals. So macam ni lah. Okay. So ni ada table dia sebenarnya. Okay. Alright. So we done with digital to digital conversion for digital data. If you want to transmit it using digital transmission, right? So now we want to go to another section of our lecture, which is we want to send an analog data using a digital transmission, analog to digital. So we need to do analog to digital conversion. So previously, we convert digital data to digital signals, right? So now, digital data can be, like I said, a text, right? Let's say we want to send a text like in an ASCII code, right? In 00 and 1s. So how about if we want to send analog signals, let's say from a microphone, let's say because analog data is, for example, if you are talking to a phone, your sound that you create is actually an analog, and also maybe a video, a color, right? So we need to change analog signal to digital data. So there is 2 techniques how we can convert from analog to digitals. So first we use PCM, very famous one, pulse code modulation and delta modulation. So after digital data are created, digitized from analog signal, only then we use the previous technique to convert digital data to digital signals, right? Okay, so before we can do pulse conversion, we need to use sampling. So line coding and block coding used to convert binary data to digital signals, right? So for voice, video created as analog signal, in order to store the recording in the computer or send it to be digitalized, we need to do what we call as sampling. Dia kena sample. Maksud analog data tu dia kena sample dulu supaya dia boleh convertkan kepada binary, right? So you see first, let's say we use first amplitude modulation. So this is how we do the sampling. So for example, we have an analog signal here. So in PAM, pulse amplitude modulation, the sampling means measuring the amplitude of the signal at equal intervals. So from here, you see the signals, the variation of signal, the unlimited kind of signals, we measure the amplitude and we get the values here. So for here, we use PCM, modify the pulse created by the PAM and complete a digital signal. So we quantize, so kan kita dapat macam ni, so kita tengoklah, okay. So untuk plus 25 amplitude, so dia dalam values 1 to 4. So kita daripada situ baru kita convert dia kepada nampak binary. Okay, so here how we convert from analog to binary data. Okay, so here we can see how it's changed. So you can refer it back. So actually it has a table. Okay, so in PCM it's made up of PAM. Right, so the PCM, actually the first step is quantizing is by using a PAM, pulse amplitude modulation. Then it's quantized, so from the PAM, right, so from the PAM we get here, right? So from PAM we get here, so from the PAM it's then quantify, so supaya kita boleh quantify lah sebenarnya untuk amplitude positif 25 ke, untuk positif 50, berapa dia punya values tu, so dia quantifies. Dan later on, bila dia dapat values tu dalam table ni, baru dia akan tukar kepada binary. Daripada binary encoding, of course, kita nak transmit di digital, kita just guna line coding lah. Macam sebelum ni yang kita belajar Manchester, ANZ, bipolar, itu adalah kita line coding scheme. Right, so this is the ni. So for analog signal to PCM data code, so first kita tengok kat sini kita ada analog. So first we use a PAM, pulse amplitude modulation, dan kita dapat dia punya value sini, dan kita quantize, dan kita dapat macam ni. After that we turn it into binary encoding, When we get binary data, then we use a line coding and we use Manchester ke apa macam mana kita nak represent digital data tu dalam digital signals. Okay. Alright, so how we want to calculate a sampling rate in digital transmission, right? So actually we use Nyquist theorem. We already learned this in previous chapter, in chapter 2. So we have Shannon theorem and Nyquist theorem. So if it is a noiseless channels, so we use Nyquist theorem. So according to Nyquist theorem, the sampling rate must be at least 2 times the highest frequency. So kalau kita nak tahu sampling rate dia, so kita tengok the highest frequency, okay, so kita times by 2. Right, so let's see the exercise here. For example, it have a bandwidth of dia punya antara 1000 to 1010. So ni bandwidth dia lah. So bandwidth ni sebenarnya 1100 ni, 11,000 Hz ni kita tolak dengan 1000, kita dapat 10,000. So kalau nak tahu dia punya sampling rate, so 11,000 ni the highest frequency ni kan. So kita times 2. So kita dapat 22 sample per second. So inilah kita menggunakan Nyquist. Right. So next, okay, boleh tengok sini juga. A signal is sample. So each sample requires at least 12 level of precision, 0 to 35 and negative 0 to 5. So how many bits should be sent for each samples? So ni adalah, so we need a 4 values, so 1 bit for the sign and 3 bit for the values. So 3 bit value can be represented 2 to the power of 3 levels. So 000 to 111, so which is more than what we need. So supaya dia boleh represent yang ni itulah 12 kan? Betul tak? Pasal okay. Pasal daripada sini nampak kita represent lebih ni je tu. 111 ni kan dalam binary ni 1 tambah 2 tambah 4 berapa? So kita boleh represent. So we more than we need. So a 2 bit value is more enough. Saying 2 to the power of 4 and 4. So bit value is too much because 2 to the power of 4 is 16. So membazir lah. Okay. And also alternative to PCM, alright, macam mana kita nak buat dia punya analog to digital conversion tu. So tadi kita belajar PCM. So now we go into delta modulation. So for delta, PCM is a complete technique. The delta modulation is simplest, right? So PCM find value of signal amplitude for each samples. So for delta modulation is it find the changes from the previous sample. So itulah nampak pun delta. So delta ni maksudnya dia tak tengok amplitude, dia tengok the changes tu. Okay. So contoh kalau ada change in the value, dia tengok dia punya difference of the changes lah. Okay. So kalau tengok dalam data modulation yang komponen, so kita ada analog signal macam ni. Okay, dia ada satu comparator, dia tengok kalau dia punya value tu different, baru dia akan cari dia punya differences. Okay, right. So the monitor at the sender to create a bit stream for analog signals. The process record the small positive or negative changes, right? Called delta lah. Okay, so this is how we do it. So you can read on your own, and we will do the PCM and data. We will try to do it in our tutorial. Okay. Next, okay, this is the bit rate. So macam mana kita nak calculate dia punya bit rate. So daripada sampling rate, kita darab dia punya bit per sample tu. Dan kita dapat dia punya bit rate. Okay, so if we want to digitize the human voice 0 to 400 Hz, so what is the bit rate? So assuming 8 bit per second, so kita dapat dia punya ni tadi. So 4000 highest tu, kita darab dengan 8 bit, dengan 2. So kita dapat 8000 samples kan. So ni Nyquist. Okay, the highest frequency kita darab dengan 2. So kita dapat 8000 samples. So untuk dapatkan bit rate, so kita dapat daripada sampling rate tu, okay, so kita darab dengan 8 tadi, 8 bit per samples. So we get 64,000 bit per second, dan we convert kepada kilobits. So 1, 2, 3, so kilobit. So 64 kilobit per second, right? Okay, next, the last section is, so now we already discussed about, okay, so how we transform from digital data into digital transmission, analog data into digital transmission. So now, if we want to use a digital transmission, what is the transmission mode? So bila kita nak transmit tu, dia ada transmission mode dia dalam digital transmission. So in data transmission, we can do parallel or serial, and the serial is further broken down into synchronous and asynchronous. Okay, so parallel transmission that means dia hantar serentak lah, nama pun parallel kan. So maksudnya mungkin dia nak send an 8 bit, so dia ada 8 wire, so 88 tu akan send 8 bit together lah, the group macam ni. Right? Okay. So advantage of course speed, pasal untuk send 8 bit tu dia tu hantar sekali je kan, right? Tapi dia punya drawback is of course dia punya cost, pasal dia perlukan apa ni? Dia perlukan dia punya apa ni? Kabel yang banyak lah, kan? Dia perlukan banyak channel. Okay? So speed of course pasal dia ada 8 channel, so dia boleh send 8 bit sekaligus. So but the drawback is the cost and usually used for limited or short distance. So selalunya benda ni kalau kita buat parallel transmission ni kan, selalunya dalam benda yang dekat, contoh antara CPU, contoh antara kita graphic card dengan kita CPU, so memang dia pakai parallel transmission, dekat je benda tu dalam satu sistem komputer je. Tapi selalunya for long distance communication we will use serial transmission. Right, serial transmission that means dia hanya ada satu wire dan dia send satu-satu. Contoh kita ada 8 bit tadi, benda yang sama, so kita hantar kosong dulu, 1 1 0 0 0 1, macam itulah. So transmission is based on bit, one bit by bit one at a time. Advantages of course kita just satu wire, so of course reduce cost of transmission. So it need a conversion between parallel to serial and parallel, itulah. And also kan kita tadi serial transmission is being broken down further into synchronous and asynchronous transmission. So the first one is asynchronous transmission. So in asynchronous transmission, we send a start bit at the beginning or one or more to stop the bit at the end of each byte. So that means dia ada gap. So maksud macam ni tau. Let's say kita nak hantar data macam ni kan. So contoh dia nak start hantar data tu, dia akan send kosong dulu. So kosong tu dia bukan a part of the data tu. Kau tengok sini, dia nak start, dia hantar 0. Dia nak bagi tahu supaya send receiver tu, okay aku nak start hantar data ni. So dia hantar 0. Dan selepas 0 tu baru dia hantar the actual data. 11010 tu. Dan bila dia nak stop, dia akan send 1. So between this bit group tu, dia akan gap dulu. Dia maksudnya dia akan stop dulu. Baru dia hantar balik 0 macam tu. So daripada situ baru receiver tahu dekat mana data tu start dengan stop. Bila dia nak start hantar, dia start hantar. And for another one is, this is asynchronous, and another one is synchronous. So for synchronous, so the reciprocal it is the recipe of the receiver to group the bit. So maksudnya dia hantar je. In transmission we send bit one after another without stop and start bit. So dia tak ada stop ni. Kalau ni ada gap kan. So ni tak ada. Right? So dia terus hantar je. So receiver tu yang kena pandai groupkan dia. Right? So we see the differences. So in asynchronous we have slower because of course the slower pasal dia ada gap ni. Dan even dia nak hantar tu pun dia kena send dulu kosong. Baru hantar data, baru tu nak stop, dia hantar satu dulu. So nampak tak? Untuk hantar 1, 2, 3, 4, 5, 6, 7, 8 bit of data ni, dia kena send additional 2 bit kan? Nampak? Slower but cheap and effective. So example is keyboard. Okay, but for synchronous, of course, it is faster transmission and usually useful for high speed application. Tapi untuk kita ada synchronous ni, dia kena ada satu clocking mechanism lah selalunya. Ni mungkin dia tak bincang kat sini. So synchronous transmission, dua-dua dia mesti ada some clocking mechanism. Maksudnya dia akan contoh, okay start clock. So nanti receiver pun ada clock yang sama. So dari situ dia boleh tahu bit mana. Alright. So mungkin dia tengok per millisecond ni. Contoh, okay. Contoh dia cakap kat sini, selalunya untuk hantar 8 bit ni memerlukan 1 microsecond. So dia receiver tahu, okay, next microsecond, okay, next group of bit of data. Macam itulah, dia kena ada clocking mechanism. And we also have what we call as isochronous. So in real-time audio or video, uneven delay between frame are not acceptable. So it will cause synchronous transmission fail. So in TV image, or it will have a 3 image per second. So actually in synchronous dia akan hantar it at a fixed interval tau, dalam fixed rate supaya untuk make sure yang kalau macam contoh kan, kalau kita tak synchronize kan, dia contoh hantar kan guna TV tu, kalau kita tak betul-betul, so masa TV tiba datang, bila TV dapat signal tu, dia tak synchronize betul-betul lah, mungkin gambar dia celau ke apa kan. So untuk to overcome that, it will use a asynchronous punya approach so that it can guarantees data arrive as a fixed rate, right? So dia hantar tu dalam a fixed rate. Okay. So untuk avoid the uneven delay tu. Okay. Right. So we already cover all things in our lecture. So we already learned about. So let's recap back. So we already learned about digital to digital conversion. So in here, we learned about what is the problem. We have DC problem, synchronization problem. So in order to overcome that, some encoding mechanism like Manchester, bipolar, right? So they have the synchronization mechanism to avoid those problems. And also we learn about analog to digital conversion, which we need to sample the we need to convert the analog to digital data. So we samples. So in order to do that, we can use PCM or delta modulation. And in transmission mode, we have serial and parallel, right? So in this is for digital transmission. So we have serial and parallel. So for serial, we can further break down into asynchronous, synchronous, and isochronous, right? So okay. So I think that's all for today. So assalamualaikum. So I see you guys during our tutorial. So during our tutorial, we will do all the hands-on about this ni. So kita akan tengok past year question, macam mana kita nak buat encoding, right? So kita akan buat more hands-on practice, right? So now this is lecture. So in our tutorial, we more hands-on practice. Kita tengok PCM tu semua. Okay. So I see you guys during our tutorial. Assalamualaikum warahmatullahi wabarakatuh.